Yep. All right, ready to get started? So I just want to talk a little bit about the MSF FSSHTTP, which is admittedly a bit of a mouthful. And maybe we can sort of continue a little bit of the theme from last time in talking about the relationship with this and other protocols. And actually, hopefully I'll be able to give you a little bit of transparency into what's going on here so you can sort of see what we're actually aiming to do with it all. So FSSHTTP, when you look at the documentation, you're going to find three documents. There's the main, we call it the non-letter doc. There's the FSSHTTP, and then we've got the FSSHTTP-B and FSSHTTP-D document. I'll go into a little bit, there's a bit of sort of historicalness in terms of how we develop things, which led to the structure of that documentation, and it can be a little confusing, but hopefully I can clear up some of that, and we can go into actually what's being represented there. The role of the protocol is primarily for enabling scenarios around multi-user co-authoring and lowering bandwidth and processing costs on the servers. And so it's all about transferring the least amount of data possible so that we can increase the frequency at which we load and save, and therefore once you've done that, you start to get interesting, you can do it very quickly so you can do the sort of multi-user scenarios. So we'll talk a little bit about what it is, the various documents. There are various components to the FSSHTTP layer. Some are sort of easier to grok than others, and I want to concentrate on one of the more complex areas, which is called the cell storage layer. And this is the actual, this has the mechanics of doing that incrementalness back and forth, and so I just want to dig into that a little bit. And talk about some of the layers that exist in there, do a little bit of an example of how sync works, and then we can take any questions. And feel free to interrupt me at any point to ask for clarifications. So, as you're aware, it's primarily for file access, and it defines a locking model for being able to put locks on files to enable these multi-user scenarios. You might ask why not just use DAV? There are a few key differences that are important to consider. The first one I mentioned, which is that we need high-frequency sync, and DAV constrains us, for the most part, to downloading and uploading whole files. And as the file size increases, especially in applications that expect file sizes to be quite large, OneNote's a great example, you just can't scale that kind of system. The other thing is we need richer locking semantics. When you look at the FSSHTTP documents, you'll find a great deal of explanation about the different types of locks we can take. And I'm not actually going to go into that in a great deal of detail here because the documents actually it's a relatively good explanation in there about sort of the semantics. But the main crux of it is there are two different types of locks. There are exclusive locks, which are very similar to what you can do in DAV and the FPSE stuff. But there's also a shared locking mechanism where multiple clients can take locks, take the same lock as other clients have to coordinate the co-authoring session. And there's a bit more in there about being able to actually log who the user is that's taken the lock so that we can enable some of the features that show you who else is in the document and some other locking stuff. I'd highly encourage you to go to the documents and read the summaries on those because they're quite thorough. The other sort of difference from traditional DAV is that in addition to accessing the actual content of the document in this incremental way, we also need a place to put all of the metadata that's associated with these multi-user scenarios. The rich client, actually Word and PowerPoint, they have a schema and a structure for describing the locks. They're a different kind of lock, unfortunately. The regions of the document in which other users are working. And that's application specific, and it's detailed in, actually I can't recall the documents offhand, but we can make this, they're available on MSDN, that describe the structure of the co-authoring metadata that these applications use. And at the end of the day, it's file content that needs to be replicated up to the server, and we need somewhere to put that. And the FSSHTTP protocol defines a file as having a file content and then these auxiliary, what we call partitions, that are other areas of the file, which I have a good diagram actually, go to this in a second, other parts of the file that can hold that data. And here's sort of a overview of what the relationship between the client and the file on the server looks like, where you've got the main content, but then you've got these other partitions that effectively just hold file state, but they're not considered by the server to be the actual user data. But they're solely to enable these multi-user scenarios. And then, of course, we've got the lock state. Yeah, go ahead.
This metadata is persistent, or it's just like?
The question is the metadata persisted or is it memory-based? To a large degree, that's up to the server implementation. The protocol defines the durability expectations of that data, but the durability is nowhere near the same as is required, obviously, for the main content. And so SharePoint 2010 does actually store that data, the partitions in the main content database, so it is durable. But there are processes that clean that up after a while, so the durability isn't the same as the main content. But certainly other implementations could store it in memory if that was a good trade-off. Getting ahead of myself, so I'm just going to go back. Sorry, I'm going completely the wrong direction here. Okay, so basically the incremental sync, you've got locking and you've got this partition support. And so when you actually look inside the protocol, the first thing you see is a mechanism for just packaging requests, or you can think of them as sub-requests. The term request is server-loaded, but they're the verbs that the protocol supports. And the FSSHTTP, without any letters on the end, describes that packaging mechanism. And you can think of it literally as a given round trip or a given overall request to the server contains multiple sub-requests or requests. Those can be, they're all directed at the same URL, the same file, but the requests can be either independent or they can be dependent on each other. So you could have a lock request in there followed by a file download request, and you could say, only do the file download if the lock request succeeds. The rich clients actually use that to structure sort of how they want to go about taking locks and then downloading the content. And the requests in there can span the various partitions in that exist for the file. And then we define, so once we've got that request packaging mechanism, we define a set of requests, and the requests come in different categories, if you will. There are the locking requests, there are the sort of co-authoring specific requests, and then there's a set of requests that are referred to as self-storage requests, and these are all of the ones that are to do with the incremental sync of the file content. And that's sort of what I want to dive into in the rest of this talk, because as I say, the locking requests will be somewhat familiar, and the co-authoring ones are relatively straightforward as you read through. Make sense so far? Yep. I can't operate this thing. So as I said, there's a little, the documents, the organization of the documents actually requires a little bit of explaining. When you look at the FSSHTTP one, you'll find that it's the format of it is very XML based. The schema is all in terms of sort of it's SOAP inspired and breaks down into a set of XML schema for describing this packaging mechanism and for describing the various locking requests and the co-authoring requests. It also has a section in it that describes how a binary blob is embedded. If you then go to the FSSHTTP document, we describe the schema for that binary blob. That describes another packaging mechanism, and then a bunch of requests that are all about this self-storage layer, which we'll get to in a second. The reason why we have binary at this level and XML at this level is there's a bunch of pragmatic things. There's a bunch of pragmatic aspects to that. The main one is that we end up with a lot of actual binary content data in the self-storage layer, and we wanted the most efficient way to be able to represent that, and encoding it in the XML was actually going to be very inefficient and take away a lot of the wins that we were after. That's why these two layers exist. It's a little confusing, but because you've effectively got two mechanisms for doing the same thing, but there's sort of a really good reason why we chose the different encoding. So you could think in a theoretical way that these are very, very much related, but they're just different encodings of effectively the same kinds of mechanism, if that makes sense. If you then jump to, sorry, go ahead. Oh.
You said like you use some kind of special command for passing binary. Why you wouldn't use like mtom message, for example, so-based?
Good question. So the question is, why don't we use mtom encoding within the FSSHTTP protocol for the binary parts we make? So the answer is we actually do use an mtom encoding in the FSSHTTP protocol, and the issue is that there's two things we're representing here. We're actually representing the JPEGs and images and text content that might be part of a Word document. But we've also got a lot of structure, metadata structure that defines that data, and that by itself, if we encoded that structure as XML and then referenced the larger binary payload, we still found that the overhead of that XML encoding was quite significant. OneNote actually breaks its structure down into a very small level of granularity. And so the overhead of that XML description could sometimes be as large as the data we were describing, and especially an mtom reference. And so it just made this very inefficient. And so what we really needed was a way of encoding that metadata and the binary data all in one, which we can then wrap into an mtom packet that then gets encoded in mtom at this level. Does that?
Yes.
We wish we could. It would have.
Like you have small pieces of data, so you have a lot of overhead.
Exactly. Yeah. The last document, MSF SSHTTPD, is a description basically about how you use the other parts of the protocol stack to encode any arbitrary file content. And I'll have a diagram a little later in the deck that will show that relationship, so make it a bit more clearer. But you can think of this document as being a client of the others. We're sort of using our own protocol and describing how we've done that. Okay, so am I going backwards or forwards? I am going backwards. I'm going forwards. So, concentrating a bit on the actual file synchronization part of the stack. This is all in what's known as the self-storage layer, so when you see references to that in the documentation. This is mainly all described in the MSF SSHTTP document, but you'll find some references in the main document as well. Let me see. So we end up with this layered system where we have a set of, we represent data as in a set of layers that goes from most basic and optimized for sync and storage into intermediate layers that start to represent some of the structure of the file, all the way up into the actual file that the application can consume. And I'm just going to jump straight to this diagram. There's a lot of jargon in here, but the thing I want to sort of illustrate is that these documents define various parts of this layer, and the layer at which you might be interested in working can define, sorry, let me repeat that. There are various interesting things you can do at these layers without having to understand all the other layers. It's a relatively complex stack because it's, at the end of the day, solving a relatively complex problem, but that doesn't mean you have to interact at all of these layers. And you can sort of see up at the top, we've got the actual server, and at the bottom, you've got the application, the client. And the server basically is storing blobs and key value pairs. the client is consuming, in the case of Word and PowerPoint and Excel, a doc or a docx, and then the two intermediate layers here, the FSSHTTP, defines this thing called the data element graph that we're actually going to dig into, and the thing that another layer that builds on top of that that defines a lot of the relationships between parts of the file in terms of how they can change. And then the FSSHTTP document defines how we then use that to represent a file. It's difficult to explain, but the sort of key message I want to get across is if, say you're building a server or you're building some kind of caching or optimization solution in that, on top of the server, you can work purely at this level and understand a relatively constrained part of the contract, and the rest of these layers will sort of just talk to that. Things get a bit more complicated if you're building a client, because then you have to actually implement the D part of the protocol and more of the B part. But I just want to encourage you, when you look at the documents, there's a way to tease it apart and then examine your scenario so that you don't have to actually implement everything in the documentation. Does that kind of make sense? Again, I apologize for sort of putting a lot of jargon on this slide, but when you look at the documents and then come back and look at the slide, they'll kind of give you a good overview of where you are in the system. And as I say, I want to sort of go straight into the storage layer, because there's actually, you can do an awful lot here, and it's probably the easiest to explain in the time that we have available right now. So I covered a lot of ground there, and it's, as I say, it's difficult to explain. Any questions at this point before going forward? Yeah.
So the FSHTTP encapsulate FSHTTP in it, like it's just like one type of objects that you invested in representing, like the file object, or?
So basically, you can think of the base document and the B document as defining a way of representing files, right? And at the end of the day, it's a graph structure, and that offers various primitives into which you can put data. And then, so once you've got that system, there are any number of ways of taking, say, a Word document and representing it in that. The key is that we came up with one that we think's good, and if you want to talk to, if you wanted to talk to, say, a SharePoint server into which we put a Word document using that schema, you'd need to use the same schema, and the D document describes that. And
so you used that model, but you could have chosen another.
We could have chosen another. OneNote uses a slightly different schema, and that requires, interacting with that particular schema, which is very similar to the OneNote file format. But for Office documents, and indeed any other document that we call a generic document, you can use the D document to explore it. If that makes sense. So digging in. So at the end of the day, there are these various layers, but it all boils down to a directed graph of two types of node. And stop me at any point, ask questions as we go, because I'm going to go through an example, and it's better to elaborate as I've got the various slides up. So this graph, there are these two types of nodes. We call one index nodes, and we call the other data element nodes. And there are various derivations of data element node that carry different types of data, and those are described in the document. But right now, we really only need to look at the base class and just call them data elements. They have two, they're different, and they have the two different types of node have different properties that are kind of important. The data element nodes are immutable, and they carry the majority of the user data and the larger parts of the metadata. The index nodes are mutable, so they can change, but they carry very little data. In fact, they end up being just these key value pairs, you can think of them as. All the nodes have IDs that are GUID-based. We actually use a slightly larger GUID than a 16-byte GUID. It's a GUID plus an integer. The reason for that is that they're more compressible. If you use the same GUID component and you've got sequential integers, you can compress those. the documents then define a model for serializing these data elements into binary blobs. And the index nodes can just be represented as key value pairs. So at the end of the day, you've got a bunch of blobs and a bunch of key value pairs that represent this graph. So then sync, and a lot of the protocol that's about loading and saving is basically about syncing and receiving and pushing changes to that graph. So you've got new data elements, because you can't have changed data elements, they don't change. You get new ones or you get orphaned ones. And you get updates to index nodes, because they can change. And as I said, we have various server implementations that you can very easily imagine how you store this kind of data. You can put blobs in a table, and you can have a table for key value pairs.
So how do you choose the nodes?
So so the question was, how do you choose the nodes? Remember back in this diagram, it's actually this layer that chooses the node. So this storage layer really is just that data element graph. And then the cell layer defines how it wants to use that data element graph to construct yet another representation. So this is sort of the mid-tier between here and the thing. I'm skipping the question in a way because it's a long answer. The documents go through a lot of that. I had to choose something on here to focus on, so I wanted to stick to the core piece. But go to the documents and you'll find a long explanation of the different types of data elements and what they represent. Again, apologies for not being able to fully go into that. The immutability of these data elements is a big thing. You can use it and the fact that they're globally ID'd, that's something that we leverage a lot. So, quick example. I'm going to do it for time. So this simple graph, I've got my IDs on each of the nodes. These are meant to be GUIDs, but I wanted to make them a little bit more readable. Index nodes are very simple again, because really they just contain edges. They're key value pairs. Data elements, I've got some basic data in my data elements. We don't actually do this. This is a simplification just to illustrate the point. So hopefully this animation will work. So let's take a server and a client. The client hasn't downloaded anything yet, so it has no state. The first step is for the client to make a request, and you'll see that there are really two main types of requests in the protocol, a query and a put, and load uses query and save uses put. They're actually called query changes and put changes, but we call them query and put. And the first query is the client makes a request to say, hey, give me everything that I don't have, and I don't have anything. So this is simple. The server will send back a set of blobs and a set of these key value pairs that represent that graph. And the client will then store this in the Office document cache, and it will use the D document to then traverse that and interpret that as a file, which it then gives to Word, which Word loads, and you're editing. So in my example here, I wanted to show what happens when changes occur on the server. So the scenario is that a user has come along on a different machine now and made some changes. And they added a new index node, and they added two new data elements that just, again, I've taken some liberties here. This is not the schema, but it's a change. And there's actually a subtle point here that I wanted to illustrate, which is we added this. So node 9 was added as a child to node 8. Sorry, I'm not going to go back because it will mess up my animation, but it was added to this data element. And you'll notice that to do that, we actually had to make a new data element node because, again, you can't change them. So this, in my previous example, had an ID of 2. It's now got an ID of 8 because it really is a new node because we changed its data. Obviously, index 1 had to node 1 had to change as well. It's not a new node because those are index nodes and we can change them. And so the set of changes that occurred here are all of the ones that have my little star on, and those go all the way back up through the parent chain. So now the client makes another request, and actually, I was going to put on this slide the details of what the client was sending, but I just have to describe it because I ran out of time. So this time the client has 1 through 6, and it can describe that to the server. It can say, hey, I query changes again. I have 1 through 6, and the server can then enumerate the set of changes that occur. It can enumerate the current state that it has, and obviously anything that is not in that 1 through 6 set can be sent to the client. So we do that enumeration, we send just those changes. The client applies those changes. The application is fairly easy for data elements because they're immutable. You just add them to a big bucket. For index nodes, that's where it has to, sorry, I'm losing my voice. For index nodes, if there are no changes on the client, that's easy. It just updates all of those key value pairs. But for any key value pairs that have been updated on the client, i.e. local changes, that's where the client can detect conflicts. Any questions on that? Yeah.
So, we could understand how you can have multiple data model instructions and you have people collaborating on a text document or editing different parts.
Yeah.
So the system likely split that into 2 separate blocks so that you could have editing on their own block or not, or will that change in one block?
Okay, good question. So the question is, in a multi-user editing scenario where you've got a run of text and you've got 2 people editing in different parts of that document, how will that be treated? Will it be one big blob or will it be multiple blobs? So the answer is actually how the data is split is independent of the current scenario. It's static and it's based on the schema of the document. And the D document actually describes how we do this splitting for the Office documents and, in fact, non-Office documents as well. In the case of a docx, it's based on the actual OpenOffice XML packaging format and a set of heuristics about how we subdivide a larger block. We actually use the remote differential compression algorithms in Windows to subdivide based on the actual data. There's a long way to say that it could be one big block, or it could be multiple smaller blocks, just depending on where you are in the document and the schema of the document.
So it's based on static rules.
Precisely. So it's based on static rules, so yes, not dynamic rules. And the key is that it doesn't matter from a scenario perspective, because the documents, if it were 2 blobs, we would replicate you might transmit less data, which is good. But at the end of the day, the application is still going to do a merge if the change is within the same, what we call, unit of consistency. And for the Word and PowerPoint, that unit of consistency is the entire document. Again, this is described in the D document. For OneNote, they actually define more granular units of consistency, which allow, if you're editing on 2 different pages, then you won't be merging and you will not be sending back and forth the same block. And again, that's because it's a static rule, but they divide at the page level. Does that address the question? Again, a lot of the answers here, it's complicated, and then you have to go into it. Anything else on here? Just one final, you'll find in the documents that we talk about a lot about this concept called knowledge. If you're familiar with the Microsoft Sync Framework Foundation, it's a very similar concept. Sorry, I'm closing up here. And knowledge is that mechanism that the client uses to describe its current state to the server. And it's typically ranges of the IDs that it knows about. We try to compress them down to make that knowledge as small as possible. We actually already talked to you a little bit about this. So as those client changes are applied, the data elements can never conflict because they can never change. The other changes to the index node, that's where obviously you can have two changes at the same time. We use an opportunistic concurrency check on the server. So when the server is pushing changes, the server will apply those index node updates, and if the index node is different from what the client expects, the base state, it will signal an OCC failure, which will cause the client to realize it has to do a merge. It will download, do the merge, and then push back with the new state and repeat the process. My deck didn't get completely updated. I'll have to do these off memory. So when you're looking at the protocol stack, there are a few considerations. The first and most important that's not on here is that it is a relatively complex stack, and the implications of getting it wrong are usually corrupted user data, and it can be insidious because it's an incremental system. So you can have corruptions that sort of get introduced into the system and are latent for a while and then cause problems down the road. So think about how you're going to test and the test suites and the kinds of scenarios, and making sure that you're covering all of the scenarios that the Office clients expect, because it takes a while. The other thing is that we rely a lot on the IDs that are described in the documents to remain basically stable for a lot of scenarios, and a lot of scenarios to actually work and be efficient. And a good example is that you can rename and renumber some IDs and reinterpret them, but there are often consequences from doing that, and some of them are not so obvious. You can cause excessive bytes over the wire and a lot of churning across the network. We've done this ourselves internally. It's very easy to make a change and look at the system and be like, "Ah, great, it works." But then suddenly you look at the netmon capture and there's horrible traffic going back and forth. And so you need transparency into the lower level of the system to know what's happening. And you need to measure it, and you need to have metrics. And we spent internally a lot of time doing that so that we understand what's going on. The other thing to mention is that, again, because you can see that what's going back and forth are just these data elements, just these blobs, you don't have a whole view of the file at any one particular point in time in many scenarios. So if you're just looking at traffic coming across the wire, you have no way to know what the entire state of the document is. So if you have a scenario where you want to do some analysis at, say, the docx level, that can be tricky. It's not impossible, but it has implications on how the system works, because you need to go and get that other data from elsewhere. And so that can mean that you have to reassemble the whole file at a point in time where it could actually have a cost on the system. Just something to think about. It's okay. That, I think, brings me sort of to the end of that. I know we feel there's some questions on the way. Any clarifications or things you'd like me to go into? Yeah.
For the client merges,
Yeah.
anything that's specified in the generic layer is designed up.
So the question is, for merge, is there any sort of generic mechanism there, or is that all app specific? The answer is it's all app specific. The FSS protocol doesn't define merge semantics for the clients. They are responsible for doing that themselves. And it all happens on the client when they do that put changes and that OCC check fails. That causes them to run merge. Actually, it first causes them to download the changes that occurred. The Office document cache already has the previous base version that the local changes were made of, and it will then do a three-way merge and then repeat the process to go back to the server. There are some protocol, and you'll see in the B document, allows the file to be split into different units of consistency, we call them. And if changes occur in two different units of consistency, there is no merge triggered. So that can be one way to avoid merge, but if merge actually has to happen, it has to happen on the clients. Yeah.
Until the office finds all the rich lines, then do they constantly server to find out? Or is it something
So the question is, do the rich clients constantly poll the server to determine changes? It's complicated. In general, yes, they poll the server, but there are mechanisms that exist sort of in that co-authoring set of requests that we have that allow you to actually throttle back your poll rate. And there's a service called Am I Alone that allows you to determine if there's anybody else in the document. And the Word and PowerPoint will actually use that to know that really there's no point in going and polling. And they'll throttle back their requests. So while there are active editors in the session, yes, they're polling at a regular frequency. OneNote polls more aggressively on the main content because it doesn't use the metadata partitions. The rich clients poll on those the Word and PowerPoint poll on the metadata partitions much more frequently than they do on the content partition. One thing that is assumed in the system is that a poll for changes when there are no changes is cheap, and that's something that the server can answer very quickly. So, any other questions? So the question is, what does it give you to poll frequently when there are two people editing the document? It comes down a lot to user experience. The longer you go without getting changes, the more you risk a more complicated merge. In OneNote, for instance, the result of a conflict in merge is a conflict page. So it pushes the changes you just made into this sort of shadow page that you can get to in the UI. But if you're in a session where a lot of things are happening quickly and OneNote was being vigilant, polling frequently, you would see the other person's changes coming in, and you'd make your changes on top of those, thereby avoiding the merge. But if you went for minutes and a lot of changes had accumulated, you could find that the merge was quite unpleasant. So, yeah, exactly. And that A, people tend to like that, and B, it avoids this downstream merge. The Word and PowerPoint operate a little bit differently because they're more optimized for a document-based experience where you don't necessarily want the whole document changing under you all at once, whereas OneNote's more notebooky and you kind of do want to see everything changing at once. So it depends a lot on the user experience. Do you have a... Yeah. So the question is, the protocol doesn't support versioning or checkout, and do we have plans? I guess that sort of a high-level way to answer that is that you can see that the protocol at its high level is this generic request mechanism, and so we can very easily add new requests into that. And we will do for new features, and we're looking into combining more existing functionality like check-in and check-out into that. We can't promise anything just yet. There are advantages for doing that because we can do it all in one round trip. So it's one way for us to actually lower the cost on the server. As I said before, we're not innovating in the other protocol space for those features. So you should expect innovation in the FSSHTTP space.